So we said that we will focus only on decision problems. So the answer is always yes or no, and we defined our DFA, NFA, epsilon NFA accordingly. And later also we will define this push down automata, Turing machine, also in a fashion that the answer is always yes or no. But in today's lecture, we consider a type of actually two types of deterministic finite automata which has output other than yes no. So there are they are basically DFAs. The transitions are deterministic, and there are two types. One is called Moore machine, another is called Mealy machine. So how do they provide output? So this Moore machine, whenever it reaches a state, so what does the DFA do? It jumps from states to state, right? So this Moore machine is such that whenever the machine reaches some state, it immediately emits or outputs some symbol. And this Mealy machine is almost similar, only the difference is that it outputs a symbol while making a transition. Okay, so while it is making a transition from one state to another, so during that transition it emits output symbol. So we already have symbols for input, right? The set of those symbols is called input alphabet, right? We used sigma for that. Now here we are considering another set of symbols, right? So output symbols. So we are considering output symbols, which can be different from input symbols. So we need another set of another alphabet. So we will call that output alphabet. So as I said, both machines are deterministic, and also there is a crucial difference that these machines do not have any set of final states, right? So in DFA we had this F, right? Some set of final state which is some subset of Q, right? But why did we require this F? Because this F determined whether the output was yes or no. Okay, at least for DFA it's a direct relationship. I mean, if you reach some state in F, then the answer is yes, otherwise the answer is no. But here, I mean, we have a more general way of providing answers. We are outputting symbols at each transition, after each transition. So we do not really require this F to tell us yes or no. So this F is not required, and this F is not there in either of this machine. So let us just see in more detail how these machines look like. So let's consider Moore machine first. As I said, it outputs symbol when it reaches a state. So this is how it looks like. So if you see this is just a DFA. Okay, you see that there are states, there's a start symbol Q0, and there are transitions, and the transitions are labeled by input symbols. So here this A, B is input symbol, right? So we have this input alphabet sigma, which consists of this AB, right? And we have start states Q0, this capital Q for set of states, and transition function as we learned it for DFA, right? Now it also has this boxes, right? So this means whenever the machine reaches this state, it will somehow output this 3. Whenever it reaches this Q2, it will output this 1. So the output can be either say 1 or 2 or 3. So this 1, 2, 3, they constitute the set of output symbols. So this is called output alphabet delta, right? So here we are talking about two alphabets, input alphabet sigma and output alphabet delta. And as I said, each state has an associated output symbol. So we have a mapping from state to some output symbol, right? So we have something like this. So this Q0 maps to 3, Q1 maps to 3, Q2 maps to 1, and Q3 maps to 2. So we just name this map as delta, lambda. So what is the signature of this map? So it takes a state and it gives you the corresponding output symbol. So that is why it's delta. It's delta, not sigma. Okay. So this is important. And how does it provide output? So consider the behavior of this machine on this input. Okay, this A B B A. So this is coming from sigma star, right? So it's a string over input alphabet. Now if you see the transitions, so you start with Q0. So on A you go to this Q1, right? And then on another A, from here you go to say Q2. So from here on B you come to this Q3. From here again, if you see a B, you take this H to go back to Q0, and then again on A you come here, again on A you come here. So this is the transitions, right? This is the sets, this is the states that you go through, and these are the symbols, input symbols on which you are making the transitions. Now as I said, if you are in Q0, you immediately output this thing. So as you are processing this input, you are also emitting the output. So when you process, so when you even haven't started processing anything, so you are in Q0, right? So you are in start state and you haven't seen any symbol yet. So since you are in Q0, you emit this lambda of Q0. You emit this lambda of Q0. So one characteristic is that the first symbol is always this lambda of Q0, right? Doesn't matter what the actual input is and what is coming next, irrespective of the input. Whenever you start this machine, it immediately emits this lambda of Q0. Okay. So then it makes this transition. So it emits this lambda of Q1. Then it makes this transition. Then it emits this lambda of Q2. So one by one, it gives you this output symbols as it is processing. So one point to notice is that, as I said, the first symbol is always this, which is independent of the input. And also, if you have, say, an input of length n, okay. So here, if you have n symbols, say here you have n symbols. So then how many states do you have here? So here you will have n plus 1 states, right? So that means here also the output will be output will consist of n plus 1 output symbols, right? So for an input string of n symbols, you get an output of n plus 1 output symbols, right? But the first symbol is known. It doesn't depend on the input. Okay. So now Mealy machine, as I said, it gives you the output when it is making the transition. Okay. So what does that mean? Again, we have set of states, this Q input alphabet, sigma, start state, Q0, everything is similar as, so this part is actually similar, same as the DFA that you learned before, this transition function. And like this Moore machine, you also have this output alphabet, delta. So again, we are just outputting either 1 or 2 or 3. But now, how do you decide when to output what output symbol? You see, you need to consider a transition, right? So these transitions are already labeled by input symbols, like in DFA. So on B, you make a transition from Q0 to Q0. On this A, you are making a transition from Q1 to Q2. But these transitions now are also telling you what output symbols to emit, right? So that means, how can you determine the transition? So if you know the current state and the next the current input symbol, right? So since this is a deterministic machine, you cannot have two say outgoing edges labeled with this input symbol A, right? So if you are here, and if I say that, okay, the next symbol that you are supposed to process is A, then you have to take this path. There is no other transition. So the transition is completely determined by the current state and the current input symbol, like delta. But here we are so this lambda is telling you what should we emit as output, right? So yeah, so this means that you have a current state Q, and the next input symbol is, say, A. So while making the transition according to this delta, you also output this output symbol. So yeah, this is explicitly written here. So so this delta tells you that if you are in Q on input symbol A, you make this transition, right? And this lambda is telling you that while making this transition, you output this symbol, lambda of QA. So that's it. So both delta and lambda has the same domain, but this gives you a state, this gives you a output symbol. So here or here we are drawing this as this. So we are labeling this transition with both this input symbol and the output symbol. Okay, so this lambda QA is the output symbol that it's emitting. Okay, so here it uses semicolon, here it uses slash. This doesn't matter. The only point is that you should have two labels here, one corresponding to the input symbol that you are processing, another corresponding to the output symbol that you are supposed to emit or output. Okay, so again consider this input. Okay, so as before, you are making these transitions from Q0 to Q1 to Q2, Q3, Q0, Q1, Q2, like this before. But now the output are determined by this. So what is this transition? So it's this transition, right? So you are processing A, and while processing this A, you are emitting this 3. So that is why you have this 3. So this comes from here, right? Then you make this transition. While making this transition, you emit this one. So this one comes from this. So again, this 3 comes from this. So and so on. So you get this idea, right? How this Mealy machines work. So now formally, how to define this thing? So this is, so the DFA was defined as a 5 tuple, right? This Q, sigma, delta, Q0 and F. So here you have this Q, sigma, capital delta, okay, then this small delta, then you have lambda, and so lambda, and then you also have this Q0. right? So this sixth tuple determines this Moore machine. And also here you can use a sixth tuple. So again you have Q, you have sigma, you have delta, you have small delta, you have lambda, and you have Q0. So again this sixth tuple completely defines this machine. The only difference is that here the signature of this lambda. So here lambda is a map from Q times sigma to delta, and for Moore machine it's simple, it's just a map from Q to delta. Okay, so this is the difference. Otherwise now the question is are they equivalent, right? So this is what we are doing with all the different models of finite automata with yes no output. So we showed that DFA is equivalent to NFA, is equivalent to epsilon NFA, is anyway. So it's equivalent to regular expression. So here we have a difference that now we are talking about arbitrary sort of output, and here also we have two different models. So are they equivalent? Now here equivalence should be defined slightly more carefully, because you see when do we say that two machines are equivalent? So for yes no case, whenever one machine says yes, another says yes. Whenever one machine says no, another says no. So the output is same. So here again the generalization is that the output should be same, right? On the same input the output should be same in two machines. So then only we say that the machines are equivalent. But we have already emphasized that in Moore machine, if the input length is n, then the output length is n plus 1, right? But if you consider Mealy machine, so since we are emitting the outputs during transitions, so if you have n input symbols, you have n transitions, and accordingly you have just n output symbols, right? So here you have n output symbols. So how can the two inputs be ever same? They will always be different, right? So how can we talk about equivalence? But the point is, the first symbol in Moore machine, as we said, is independent of the input, right? It's some input which it just emits even before looking into the input, the output symbol. So we can kind of disregard that thing. So you just ignore the first symbol emitted by the Moore machine. You consider the rest of the n output symbols, and you compare that with the n output symbols of a Mealy machine. So in that sense, if those n symbols, that output string of length n over this delta, if they match for all input, so then we say that these are equivalent. So consider a Moore machine, say MR. Okay, input alphabet is sigma and output alphabet is delta. So then consider a Mealy machine, ML. Again, the input alphabet and output alphabet should be same, because on same input it should produce same output, so the domain of input and output should be same, right? And the output is a string here, right? So the input is a string here and the output is a string here. So for the Moore machine, if on input W you get this output FR, okay, and if in the Mealy machine again on input W you get this FL of W, So then they are equivalent if this is true. Okay, so that means the Moore machine will always have some output symbol at the beginning, which is independent of this W, right? So this C is output symbol which is independent of W, but then the rest should match, right? So if you remove C from this output of Moore machine, so the rest N symbols should match with the symbols outputted, which is emitted by this Mealy machine. So then we say that these two machines are equivalent. Okay. So the question is, after defining this equivalence, can we show that for a given Moore machine we can have a equivalent Mealy machine, or a given Mealy machine we can have a equivalent Moore machine? So converting Moore machine to Mealy machine is easy. Converting Mealy machine to Moore machine is slightly more involved. Both are straightforward, but move to Mealy is kind of trivial. It's absolutely trivial. So how do we do that? So suppose you are given a Moore machine. Okay, this MR is a Moore machine. You have associated lambda r, and this lambda r is mapping Q to delta, right? So we construct a equivalent Mealy machine. So we use same state. So this sigma and delta should be same, but here we also use the same states. We use the same transition function. We use the same start state. Only we have to define this lambda for Mealy machine, because the domain here is Q times delta, right? So the way we define this lambda L for Mealy machine from this given lambda r is this. Okay, this equation. Now how do we arrive at this equation? See, the idea is what's happening in the Moore machine. So you are in some current state Q. You see some input alphabet A, and then you move to this next state. So this next state is given by this transition function delta, right? And when you move here, you also output symbol, and that is given by this lambda r, right? Lambda r of this state, whatever state you have here. So this is here. Okay. So you have a transition of this sort in the Moore machine. So it makes the output after the transition. So it makes this transition and then it emits this thing. So the idea is to push this output in this transition. Okay. So instead of having this here, you just push it at this place to get a Mealy machine, right? So it is emitting this after reaching this state, and it is emitting the same thing while making this transition. Okay, but it is going to the same state because we are using the same delta. You see that this delta are same, but just this. Okay. So by definition, this symbol is what? This symbol is lambda L. So since we are talking about Mealy machine, so this is lambda of L. Sorry, lambda of L, not lambda of L. So it's sorry. So it is lambda L of Q, and what input symbol we are looking at? A. Okay. So this lambda LQA is what? This thing, right? Whatever we were emitting for the Moore machine. So, and this is the equation here. So this lambda LQA is equal to this thing. Okay. And it almost doesn't require any proof. I mean, it is obvious from the definition itself, kind of. But if you want a formal proof, you have to use induction on the input length. So if W is the input, so you take input length and do a induction on this thing to prove that their output satisfy this thing. So this FR and FL are defined here, right? So FR is the output of Moore machine, FL is the output of the Mealy machine. So the Moore machine always have this included, so the rest should match. So basis is just this is 0, so this is epsilon. So in the Mealy machine you haven't started any transition yet, so you haven't emitted any output symbol, so your string of output symbol is just epsilon. And for the Moore machine, even without looking at the input, whenever you start the machine you just emit what? This lambda R of Q0. So this C is lambda R of Q0. So you emit this, so this condition is satisfied. And if you are using some W, you break it down into XA. You assume that your induction hypothesis holds for X. So by induction hypothesis, you already have this. And then if you have this, what will we say? This output of Moore machine on this XA. So it gives you all the output while processing this. After processing X, on whatever you get by processing X, you get all those outputs, right? And say after doing this, you reach this Q. This delta is same for both machine, right? So after processing this X, starting from this Q0, you reach state Q. So after emitting all these things, you are again emitting this in the Moore machine because of this, right? Because the next state is this, and so the next output symbol is this. So in the Moore machine, you have this relationship. And in the Mealy machine also we defined it in the same way, so that the same relationship holds, right? So again, in the Mealy machine you have processed X, so you have already outputted, already emitted this FL of X. So then you are making this transition from Q on input symbol A. So you are emitting this lambda L of lambda L of QA, and lambda L of QA is defined as lambda R of this thing. So this thing and this thing as same. And as we said, by induction hypothesis, there is a typo here. So here we have a C. We should have a C. What is happening? So here we should have a C. Okay. So there's a typo here. So typo error. So by induction hypothesis, we should have if R of X equal to C of FL of X. Okay. So this is correct. So that's the formal proof.